Take an arbitrary vector in two-dimensional space. It can be represented with the help of two unit vectors, which we usually call x and y, or e1 and e2. The vector v is written as a linear combination of these two vectors. Including linear combination coefficients 2 and 3 over 2 in this case. The two unit vectors are also called basis vectors, and the expression is also called a basis set expansion. The coefficients are called expansion coefficients. The two basis vectors form a complete orthonormal set. They are orthogonal with respect to each other, each of them is normalized, and they are complete in the sense that we can use them to build any arbitrary other vector in two-dimensional space. The same concept can be also used for functions. A well-behaved function can be represented as a linear combination of basis functions, as long as the set of basis functions is complete. For example, psi of x can be represented as a sum von n equals 1 to infinity of bn times psi n of x. Psi n are the basis functions, and bn are the expansion coefficients. Note that generally we will need an infinite number of basis functions, unlike the 2D vector examples, where we only needed two basis functions. Ideally, the set of basis functions is also orthonormal. This means that the integral over all space of psi I star of x, psi j of x dx equals delta ij. Here, delta ij is called the Kronecker delta, and it is a shorthand. It is equal to 1 if I equals j, and it's 0 if I is not equal j. Complete orthonormal basis sets are important in quantum mechanics, since the eigenfunctions of a quantum mechanical operator form a complete set of orthonormal functions. We can therefore use operator eigenfunctions as a basis to write an arbitrary function. Very often, the eigenfunctions of the Hamiltonian operator are used as a basis. For a given general function psi and a given set of orthonormal basis functions psi I, how can we determine the expansion coefficients Bn? Here is how it's done. Pre-multiply both sides of this equation with psi m star and integrate over all space. This yields an integral over all space from negative to positive infinity of psi m star of x psi x dx equals, and now comes the right hand side, sum over n equals 1 to infinity of bn times the integral over all space of psi m star of x times psi n of x dx. The integral on the left hand side simplifies to delta m n. It equals 1 if m equals n, and it is 0 otherwise. Therefore, all terms are 0 except the one where m equals n, and we get, finally, the left-hand side equals simply bm. This is how you can compute an expansion coefficient bm from a given function psi and a particular basis function psi m. These expansion coefficients allow you to expand psi as a linear combination of basis functions in the sense of the equation here on the left.